Alright, so this lesson is going to be on mutations in DNA, and you guys learned that pretty much this process is so stinking complicated that if anything can go wrong, it would basically mess everything else up, and that's mostly true. But I wanted to start you off with an example, and I can show you something. I don't know if you can still see the screen, but if you'll pay attention to this. What if I were to change, and by the way, this is my granny's broccoli casserole recipe, the one I was telling you guys about, that's absolutely to die for, my favorite dish on the planet. What if I were to change, and you may have to follow the mouse here, let's say if I change, what about this word right here? I don't know if you caught that. Let me do it again. It was that, and now it's that. Technically, that would be a mutation, but did it really change anything? I could proofread that and know that I'm still supposed to reduce the heat to a low simmer. So that's not too big of a deal. Other kinds of mutations, though, you could have would be something like maybe something more dramatic, like maybe you change this to 10. And if you change that to 10 minutes, that could change everything. It could slightly alter the recipe. We're talking about broccoli here, so boiling the broccoli time, I mean, it would just make your broccoli a little bit more soggy. It may make the texture of the casserole a little weird, but still probably going to get some casserole. I'm going to change that back to 3. Now, we start talking about genuine screw-ups, where you get wicked bad mutations. It could be with preheating the oven. It could be, probably not necessarily with this one. What if we were to say, change this to this, change a pot to a skillet, or maybe this one especially. That, if I can highlight it, I don't know where the highlight button is, would be a dramatic change and would pretty much alter, if not screw up, everything that happens after that. And that's kind of what mutations are all about. And I'm going to kind of use the recipe, let me change this back. I'm going to kind of use the recipe to show you how things can go wrong, basically, for lack of a better word. So here's mutations. Basically, the definition is any change in a nucleotide sequence. That's the nitrogen bases. Okay, don't let that word freak you out. It's just the nitrogen base order of DNA, and we call it a mutation, and there's different kinds. In fact, overall, I believe there are about 4. So any kind we call a mutation. There are different kinds. We'll work our way through. This would be number 1 here, a substitution mutation. This occurs when the wrong nucleotide gets inserted during DNA replication. So you guys learned Chargaff's rule right here. You know, A always bonds with T and C always bonds with G. What if a thymine is inserted instead of an adenine in a complementary DNA strand? For example, if it codes for a T, or I'm sorry, an A, but you put a T in its place, that could mess things up. That would be like the first thing that I did up here, where I actually wouldn't be. It would be like when I replaced this 3 with a 10. I mean, that could change things. It might not be dramatic, it might be, but that's a kind of a substitution mutation. The second kind is called an insertion mutation. Most of this stuff is self-explanatory, to be honest with you. The word substitution should tell you what's happening, and the word insertion, to insert, to put in, it should tell you what's happening. So in this case, an extra nucleotide, meaning just an extra nitrogen base with its sugar and phosphate, gets put in to the complementary DNA strand. This is during replication, by the way. Complementary DNA is the copy that's being made during DNA replication. So as polymerase, which is the one that copies it, the enzyme, as it flies down the DNA double helix, it may accidentally, put in an extra nucleotide or nitrogen base, and that could potentially cause some damage. That would be the equivalent of me coming and adding another step in here and saying that after you bake for 5 minutes or after you bake for 40 minutes and let it sit, you add another step and you say refrigerate for 5 minutes. It could be a good mutation, it could be a bad mutation. It'd be kind of weird to refrigerate the broccoli casserole for 5 minutes after you just baked it piping hot, but that's just an example. Like I said, it could be a bad mutation. For example, it could say throw out in trash can, and that would obviously be a bad mutation. Alright, and the last kind, well, not the last kind, but another kind is called deletion. Again, self-explanatory. A nucleotide is literally skipped. It does not read, it does not compute, it gets deleted, and it is not added. This can be pretty detrimental. For example, this would be like me just accidentally skipping an entire step. So I don't know if you saw that. Let me show it to you one more time. I highlighted number 3, and I just deleted the entire thing. And that could change this entire recipe. For especially if it was at the beginning, I mean, everything could be wrong. So there's 1, 2, and 3 so far. Let's look at some examples of these. Let's deal with substitutions, which were the first kind of mutation. If a substitution mutation does not affect the primary structure of the protein, remember, protein is polypeptide, they mean the same thing. So what I'm telling you is that if it doesn't change anything, then it is what we call a silent mutation. Silent meaning nothing happens, nothing changes, you don't see it, you don't feel it, whatever. I'd love to know where the highlight button is on this thing. Do you get the idea? We call that a silent mutation. So we accidentally substitute, and actually the chart down here, if I can blow this up a little bit more, will show you an even better illustration of this. So if you look and follow my pointer here, maybe I can. Yep, there we go. Alright, so this is no mutation here. Alright, so the DNA level is TTC. When it is copied onto RNA, we get AAG. That's the normal no mutation that codes for the amino acid lysine. So it's all good in the hood right there. Move over to a silent mutation, which is the one I just talked to you about. Instead of a TTC, we actually substitute the C for another T. That could be a problem. However, what you might notice, or what you might remember from yesterday, TTT will code for AAA, and AAA and AAG both code for lysine. You remember the chart yesterday, and I can pull one up if you don't. Sometimes protein synthesis chart, maybe. There we go. Sometimes the amino acids, or the mRNA will code for the same exact amino acid, and I can show that to you here. We just did AAA versus AAU or something, I can't remember. So AAA is lysine, and AAG is also lysine. So that would be a silent mutation. You're going to get the same amino acid, so the protein's all the same. It doesn't change. So let me go back to our slideshow. Now, another kind is called a nonsense mutation, and well, let me actually teach you the missense first, since missense is up here. This is a different kind of substitution mutation. It's called a missense, and it's right here. I'm highlighting the word for you. Let's change that to red so you can stand out a little bit. A missense results in the insertion of a single incorrect amino acid in the polypeptide chain. Okay, so it does not change the entire structure. Well, I guess it would change the entire structure, but it doesn't screw everything up after this. It only changes that single amino acid. For example, if you can see this here, instead of TTC, which is what it was supposed to be there, it becomes TCC. And so we substitute a different amino acid, because remember, again, this is all a kind of substitution. We substitute that, and we get a GG when we copy that down, and then that codes for arginine, not lysine like it's supposed to. But nothing else changed about the strand. We only changed one little letter, and even though it gives us a different amino acid here, the rest of the protein will copy the same, and everything before that will copy the same. So it could change the protein altogether, but it doesn't completely botch it, which is what the next one would do down here, a nonsense protein. A nonsense protein is when you prematurely terminate that protein because you coded for a stop. Like UAG or UGA or UAA, they all mean stop. So you could code for 2 amino acids, and all of a sudden, because you altered this letter here, instead of copying a T, it copied an A, that will code for stop. And that protein is done, it's wasted, it mutated in a bad way, so we call that a nonsense protein. Okay? So a quick review here. several different kinds of proteins. Mutations, substitution, insertion, and deletion, and we've only looked in detail at substitution. And when we looked in detail, we said, okay, we've got silent mutations, we got missense mutations, and we've got nonsense. Silent, it's all fine, nothing changes. Nonsense, we change everything. We stop it too soon, and it's basically useless, it's dead. And then missense, we change one amino acid and one only. And I wanted to also point out an example. You've heard of this term before, I'm sure. It's called sickle cell anemia. It is actually a mutation, but it's a missense substitution mutation. Missense. And if you recall, missense means we change one amino acid. And so this is what that could do. This is what that looks like in real life.
You know where Miss Lee's at?
And here's an example of that. Basically, we call it sickle cell anemia. It's what I pointed out a second ago. And the missense comes from a single mutated letter from the DNA copy. So instead of an A, we get a T. I don't know if you can see where I'm pointing, which codes for an A. And then that gives our amino acid a valine instead of a GLU, whatever GLU is. And that basically alters the shape of the hemoglobin protein in our red blood cells. So this is a normal red blood cell, and this is what sickle cell anemia looks like. And that's all because of a single letter changing. So you can see how dramatic this can tend to be. And we finished up our substitution. And the last one that I want to show you is a frame shift. These could potentially be the worst. This is like screwing up at the beginning, and then everything else is going to be wrong after that. Insertions and deletions are called frame shift mutations, whereas a substitution is called, or usually referred to as, a point mutation. Okay? So because they happen at a single point. A frame shift can happen all throughout, and that's insertions and deletions. They completely disrupt the reading frame, because remember, we group these in triplets, which we call codons. And you need to keep that in mind, codons. And so if it disrupts the way it reads the codons, everything will be wrong after that. So if you can follow my pointer here, you'll see, maybe I should do it this way, you'll see the original strand. I'm not going to read you all these letters, but I think the first example of a change, notice this is a C, a nitrogen C there, and the substitution, which is the one we just studied, it changes it to a T, and so it changes the actual amino acid. This would be a missense substitution because one amino acid changed. However, you keep going, and what if we were to insert an extra C right here, and you can see it right there. We insert another C. Now we have shifted every other nitrogen base down one. So the codon was CTT, now it's CCT. And it has literally changed the entire reading frame. So now every single amino acid from this point on will code differently. It will code for a different amino acid because we shifted everything backwards. Insertions can be very dangerous, very harmful, cause some serious mutations. And a deletion is the exact same thing except in reverse. Every amino acid following that mutation is going to be incorrect, and it will alter the structure of that protein completely, which will probably render it worthless. So the things you need to remember here are substitutions are called point mutations, and there's three different kinds: missense, nonsense, and then silent. And then you've got frame shift mutations like insertions and deletions. And they can change the reading frame of the codons, which messes up everything. And the last thing I'm going to throw in is, you've seen this warning sign before here. It basically stands for what we call mutagens or carcinogens. And I'll type that word, carcinogens. Carcinogens, maybe? We'll go with that. Both of these words mean the same or relatively the same, and they are any substance, I guess, that can spontaneously result in a change in your DNA. So mutations can occur spontaneously during DNA replication, or they can be the result of a physical or a chemical mutagen or a carcinogen. Diesel smoke is a carcinogen, is a mutagen. Ultraviolet radiation causes skin cancer, x-rays, asbestos, tobacco smoke, all of this is known facts. And so you'll see warning labels like this to tell you, hey, watch out, we know that this is a known carcinogen or a known mutagen, meaning it can cause DNA replication errors in some way. And that's pretty much it.